Today we're going to talk about the kinetics of a particle. And we have looked at a lot of ways to describe acceleration in the three coordinate systems. And now we're going to look at the forces that cause the accelerations. And this is Newton's second law, F equals ma. So what we need to notice about this equation is that this is a vector equation, that the sum of the forces with the vectors will equal to mass times acceleration in that same line. So the forces will have a direction and the acceleration will have that same direction. So the forces acceleration of vectors, they obviously have magnitude and direction. We have to balance them in all directions using the reference frames of x, y, z, ntb, and r, theta, z. So today we're going to talk about the rectangular coordinate system, and that's F equals ma in the x direction and the y direction and the z direction. So here are the processes that we need to use. First of all, drawing a free body diagram is essential to the proper understanding of this subject, so you definitely need to do that. We need to recognize that acceleration is in the same direction as the force, or the components of the force will have a component of acceleration in that direction. Need to count on weight and friction and springs as forces. We'll be dealing with inclined planes, so we need a little review of that. So first thing we do is define the coordinate axes. They can be arbitrary. I mean, they are not fixed to a particular XYZ coordinate direction, just as long as we're consistent throughout the problem. We need to write the equation of F equals ma and honor the equal sign. Honor the equal sign, what this means is that whatever we put on this side of the equation, we need to keep on that side of the equation. These are the forces. And then on this side of the equation, that's the masses times acceleration. So in other words, the results of the forces. We need to keep it this way, in this form, until we get all the numbers in there, and then we can do some algebra and simplify it. All right, with that, let's try a little problem. Here's a problem of a large weight being hoisted up with the tension in this direction, and it's given some details here in the problem. Is that the weight, the casting has a mass of 3,000 kilograms suspended in the vertical position. It's initially at rest. It's given an acceleration. It's basically a speed upward that it gets this speed within 0.3 seconds. And that's an constant acceleration. We need to determine the tension in the cables. All right, so let's look at this as a statics problem first. In this case, we're not going to look at the acceleration. We're just going to draw a free body diagram in statics. We're going to say that there's an mg coming down and a tension pulling up. So we're drawing this part of the free body diagram. We're going to say some of the forces in the y is equal to 0, tension is equal to mg, and we can resolve for the tension is equal to 29,430 newtons. To find the forces in the tensions in each chord, we do a point equilibrium problem from statics. We're going to say the sum of the forces in y is equal to 0. So I got a tension going up, and then components of each of these tensions coming down. So here's my 30 degrees, so I have a cosine component here, so this is an AB cosine, and then I got another AB cosine, so in this case AC cosine on that side of the equation. So those are the forces in the y direction. Now to simplify this problem, we can see that that the mass is evenly distributed and that the angles are the same, so we can use symmetry to suggest that AB and AC are equal to each other. So let us just solve then for the forces in the two chords, and then we can say AB equals AC is equal to 16,991 newtons. All right, so for statics, pretty simple. Actually, dynamics is fairly simple as well. In this case, what we're going to do is draw a similar free body diagram, but in this case, I'm going to draw a kinetic free body diagram, and I'm going to say that there's an acceleration vector as well as the two forces in there. So the free body diagram includes the forces as well as an acceleration vector. All right, let's find the acceleration. We said that it reaches a particular speed in a particular time, so we can find the acceleration using the constant acceleration equation and find out that it gets to 0.667 meters per second squared. Then the sum of the forces now is equal to the mass times acceleration in the y direction. So the sum of the forces, I got a positive t, I got a negative mg, and I'm saying that that is the mass times acceleration in the y direction. So I can solve for t. And this is t in case 2. There's not two t's, it's just case 2. T2 is equal to the mass factors out of that, so I got AY, which is 0.667, plus the G, and then I get the tension is equal to 31,430. All right, so then we can just do a statics analysis here. Because these forces are moving relative to each other, or not moving relative to each other, everything's moving up at the same rate. We can use statics analysis here and solve for those two tensions in the cables, and just by the same point equilibrium process that we did before, we find that AB is equal to AC is equal to 18,146 newtons. So it went up by a generous amount, over 1,000 newtons during the acceleration. All right, here's another problem. Here we have a boat that's moving in the water, and it's going in this direction. It's got a velocity in this direction. And what we say is that it shuts the engine off, and it was going at 10 meters per second, and there's a hydrodynamic drag force of 40 V squared that's slowing the boat down. And then we want to find out how far it moves once the speed has been reduced. So let's find our positive direction. We're going to say this is positive. That's our x direction, is going to be in that direction. We have a velocity going here, and we're going to have a displacement going here. If the velocity is going here, then the drag is resisting that force. So the drag is going to go in that direction, which means the acceleration is going in that direction. So let's look at our F equals ma equation then. I got F equals ma. I can rearrange that, and I can say the acceleration is equal to the force over the mass. Well, the force is equal to 40 V squared, given in the problem. The mass is 450 kilograms. So I have an expression here in terms of velocity squared of 0.008889 V squared. That's my acceleration. To define the distance that it moves, we refer back to some of our chapter 12 stuff, and we can say that ADS is equal to V dV. We bring the A over to the other side, and we do the integral of both those sides, and I'll say that with the integral of ds is equal to v dv, which is equal to v dv over that expression for acceleration there. Then I can take that out of the operand, or out of the integral, I guess, before I do the integration, and I get 1 over 0.0889. And then over here, the v on the numerator cancels with that squared on the bottom, and I got dv over v. And then again, we integrate, I should have said we integrate that, and then we integrate that. Okay? And we integrate this one from where I started, my speed. Since I got velocity over here, I start with 10 meters per second, and I end with 1 meter per second. All right, so again, back over here, we have the integral of ds. That's just going to be s. That's the distance we've moved. And this side, you recognize this, I hope, as a log, and this would be the log of 10. Excuse me, the log of 1 minus the log of 10. And you calculate that out, and we get s is equal to negative 25.9. And again, it's negative distance because I defined that as positive, and I moved in that direction. I slipped in that direction before I stopped, so I ended up getting negative 25.9 meters. All right, I want to talk to you about friction now, and friction seems like we understand it, and generally we do, but let's just remind ourselves of a couple of concepts. Friction resists the motion, and or resists relative motion. And I call this two kinds of friction. It's not really two kinds, it's just does different things in different scenarios. So let's say this gentleman is trying to push this refrigerator. If he's about to make it slip, we know that there's a force of friction trying to resist the motion if he's trying to push it that way. Well, we also have friction underneath the man's shoes. Basically, it's helping him move forward. So the same kind of thing, there would be slip. He would be slipping backwards if it weren't for that friction. So we have force of friction helping him go forward, and the force of friction helping the refrigerator to keep from going forward. Same thing with a truck or a loader here we've got. If he's trying to push this crate, and we know that if it's trying to be pushed this way, the force of friction is resisting that motion. On the loader, the tires would tend to go this way. He would try to spin the tires, and if there was no friction, they would just spin. And you can see our little rotation vector, but the force of friction is resisting the relative motion such that the force of friction goes this way and tries to push the thing forward. Okay. Let's talk about free body diagrams. We're just a little review of these free body diagrams. Let's say we have a box and it's sitting on the floor or a table or something like that. If it has an mg, the mg acts through the center of gravity. The center of gravity may or may not be in the center of the object. It could be off center, it could be in different places. So we'll need to be cautious about where we put the center of gravity if it could be off center. We're going to have offsetting the mg. Obviously, we're going to have a normal force. And let's say we have a force of something trying to push it in this direction, and there'd be a resulting friction force resisting that motion. So in general, then the normal is going to be equal to the mg in a flat situation, unless we added another force. And this force, let's say we add that force here, and so that means that's going to affect the normal force of mg plus F2. If this force was one force, meaning it was at an angle, it would have a cosine component and a sine component, or maybe the other way around, depending on how you define the angle. And so anyway, they could be components of that angular force, and that would be influencing both what goes in this direction as well as what the normal force is. All right, how about inclined planes? If we put a box on an inclined plane, and the inclined plane has an angle theta, we recognize by similar triangles that if the mg comes straight down, there's a vertical component and a horizontal component of the actually, it's an in the plane component and a down the hill component. That's really what I should say. A perpendicular to the plane component and a down the hill component. Well, because the angle is inside here, this is always the hypotenuse of the triangle, of the right triangle. So this would be the side opposite or side adjacent. So the cosine, in general, points into the hill, and the sine points down the hill. And most of the time we'll put that sine component operating from the mg and pointing down the hill, like I've done right here. So let's put the box right here. We got our mg coming down, we got our angle theta, and we got mg cosine theta coming into the hill, mg sine theta coming down the hill. There's always going to be a normal force, so the normal force would be pushing up, resisting. Normal force is perpendicular to the plane. Normal force would never be at any angle. The normal force is always perpendicular to the plane. And then the force of friction would be resisting the motion, which would be, if it's sliding, the force of friction is going to be mu normal. Then we may have some other complications. If it's sliding down this way, obviously the force of friction would be resisting the motion there. But if we add another force, let's say we add another force here at some angle alpha, it's going to have a cosine component and a sine component, and the sine component is going to reduce the normal force. It's lifting up the normal force. The cosine component is going to be counteracting, if you will, the mg sine theta, and so we don't really know which direction it's going to go, depending on what the value of that force is and whether it's actually pulling it up the hill or still allowing it to slide down the hill. If it pulls up the hill, then the force of friction naturally would change direction and be pointing down the hill. Okay, let's talk about systems a little bit. We're going to talk more about systems, but let's just make sure we understand about friction, and that friction can never be more than mu normal, but it can be less. It's only mu normal when it's slipping or just about to slip. An impending slip is our statics term. So that our little equation says that force of friction can be less than or equal to mu normal, obviously never greater than that. So here's a little picture here. We got an mg, a little box sitting on the table, got a normal force, and let's say we push that with a force P, it's going to have a resulting friction force resisting that. Let's solve for that friction force. It is not necessarily mu normal. Let's say that we're pushing it at 20 newtons. Let's say we have a mass of 10 kilograms and a mu of 0.5. We could say that our force of friction maximum, the maximum force of friction would be mu normal, which would be mu mg, which is equal to 49.1 newtons. That's the maximum force of friction could be. But in this case, the force pushing it is only 20, so if we sum the forces in the x, and again, we're not doing a dynamics equation, all we're doing is just finding the force of friction in a static situation. We say the sum of the forces in the x is equal to 0. I'm going to say that I got 20 minus the force of friction, and that's equal to 0. So in this case, the force of friction is only equal to 20 newtons. Okay, and we'll talk about slipping and in quite a bit more detail later, but in this case, we just keep in mind that the force of friction is just a force. It's just a reaction. It is not mu normal unless it is slipping or just about to slip.